Hello guys, it's Ert here, and this is the third episode of Rewriting Physics. And on this episode, we are going to be talking about the EM field accessories, as I like to call them, as well as the magnetic and electric dipole moments. And specifically, we have, well, obviously magnetic and electric dipole moments. That'd be P and M, respectively. We'll be looking at the polarization density, magnetization vector, and the electric displacement field, and the magnetic field strength. So electric displacement and magnetic field strength. And of course, the main topic of today, which is what we're trying to get to, we will be looking at permittivity and permeability. So that would be epsilon and mu normally. So with that being said, let us first look at the magnetic and electric dipole moments. Firstly, the electric dipole moment, because that is the thing you usually start with, charge times the distance. Again, we're only looking at the purely mathematical application of this, not the physical application. But purely mathematically, we can also use this to find a notation. So instead of actually creating a new letter for this, because it's just charge times the distance, I would like to set up diacritics to symbolize this. This will become much more important later on because of moments and lengths and areas and stuff like that. We will also use this later on to make resistivity and conductivity easier to symbolize. So with that being said, we'll symbolize the electric dipole moment as Q times a length. I'll formalize this notation more later, but that's just going to be Q times the length. And the magnetic dipole moment is current times area times the normal vector. Because the normal vector is unitless, all that matters is that we have the current, which is velocity of charge, times an area. Now, what happens when we look at the magnetization vector and the polarization density? Polarization density is going to be Q per volume. So this will be denoted like this. Again, I'm going to formalize that more later. You can see that there's a corner and this diacritic smushed together. That's where this comes from. But again, we'll look at that later. And then the magnetization vector is actually the derivative of the magnetic moment according to volume. So we'll actually change things up a little bit through that and actually use our own letters. The units for that, actually let's go with the units for all of these first. This is coulombs meters. This will be coulombs per seconds times meter squared. The polarization density should be, let's see, coulombs per meter squared. And the magnetization vector will be coulombs per meters seconds, of which is not actually the magnetic field. I almost made that mistake. I'm sure it's probably going to end up being a popular mistake to make, but no, it is not the magnetic field. However, we do actually have a symbol for this, and it is a frequency. So that is a frequency by negative charge. And the way we can see that is frequency is 1 per second, and meters per coulomb is reversed. So we would be looking at 1 per second, meters per coulomb inverse for the units. And you can see those match. Yeah, so now all we have to do is look at other notations. And we notice that polarization density and the electric displacement field have the same units. Thus, this pretty easily just becomes charge times area per volume. And then will be the H field, of which just has the same units as the magnetization vector, if I can pronounce things. So again, that just becomes frequency negative Q. Now for the fun stuff, let's look at permittivity and permeability. So we can see permittivity is the units of the displacement field over the electric field. And thus, we have a little bit more calculation to do. This is coulombs per meter squared. It's kilograms per seconds, per kilograms per second squared meter per coulomb. So if we do all of this math correctly, okay, so that's what it would be in SI units. However, again, we would like to change things up and completely remove the meters out of the equation. Thus, this should be kilograms coulombs per second squared. About went over that. Meters per coulomb. Actually, you can verify this does hold, by the way. So with that being said, we'll introduce another diacritic, and that is the bar. Putting a bar over anything just makes it into its own reciprocal. So this is the reciprocal of force through 3 charges. And sadly, permeability we'll just have to use mu. But we will still calculate this and see what units we have. So with that being said, okay, this will be B over H. So we get kilograms per coulomb seconds over frequency, so that would be coulombs per seconds meters. So we get kilograms times meters seconds per coulomb squared seconds. And with that, we get kilograms times meters per coulomb squared. If we completely remove the meters, that's kilograms per coulomb times meter per coulomb. So with that, we get the definition. Permeability is mu 1Q. And we will formally define mu in units to have SI units of kilograms per U times meters per U to the N. And the last thing to mention in this video is susceptibility. And because susceptibility is unitless, I will define N as the unitless object equals just nothing times meters per U to the N. There we go. There we go. That works. We will remember susceptibility is the magnetization over the magnetic field strength, which means that we can write that as, there we go. That is how we can write susceptibility in this notation. I had to screw things around a little bit, but it still kind of works. So there's susceptibility. We have found permeability, permittivity, and the electric displacement field, polarization density, the magnetization, and magnetic and electric dipoles. And with that, the last little part of this video that I want to do is formalize the length, area, and volume diacritics. Instead of having our own letter for density, we're going to use diacritics to represent density. That being said, this is density of length. So actually, I will use x here. Equals x per length. And x, this is x times length. This is x over area. And this is x times area. And then we will also show volume, x over v, and x times v. And in this series, we'll also be putting a tilde above our v's when we are representing volume. I know that was shown a little earlier, but yes, that's what our tildes mean. So that will be our formal definition for length, area, and volume. And of course, we can combine these diacritics. That is why they're set up this way, to be able to be combined, so that when we are working with resistivity, we can multiply by A and divide by L. Thus, we can multiply by A and divide by L, and I will also, even though we already talked about this, I will write x bar equaling 1 over x. The other way that I will sometimes write this is by including a stroke. That means the same exact thing. It just looks better on some letters, especially when you need to use vectors. So with that being said, we can find resistivity as resistance times area per length. If we want to find conductance, we can flip R over, where you can flip resistance into conductance. And then conductivity, we've done this. Now we want to multiply by length and divide by area for conductivity. Next, I would like to add a couple of other diacritics to this notation. We won't be using them this video, but we will be using them when talking about light. So with that being said, I would like to first start off with, if I can write, with x over theta, so x over an angle, x times an angle, then x over a solid angle, so that would be that, x over a solid angle, and then x times a solid angle. So that would be x times a theta. And as I showed with resistivity and conductivity, you can combine these diacritics. And I will explain the rules on how to do this so that you're not second guessing yourself. And I would also like to mention how the stroke or the macron work with the other diacritics. Okay, let's try this with resistance, resistivity, conductance, and conductivity. So we start with resistance, which is of 2Q, and we recognize that this is kilograms times meter squared per second coulomb squared. We're not going to look at how to get resistance, we're just looking at the units right now. And so when we do resistivity is resistance times area per length. So with that being said, our diacritic on top will divide by length and multiply by area. And then we would like to find conductance first. So we just flip R over, R to Q. So the macron flips the letter and the number with the unit. So this will just flip the units upside down. So it'll be seconds per kilogram, meter squared, coulomb squared, just like that. That'll be the units for that. And then we'd like to find conductivity. So we flip this over. Well, we flip resistance over to get conductance. Then we multiply by length and divide by area. And actually, we don't really need the units for this. I'm going to do the formula here instead. So that would be conductance times length per area, which should be 1 over the resistivity. There's a beautiful symmetry in this notation, and that is when you write the macron on a letter, so when you flip it over, you just vertically flip the diacritic that you're using. So you'll see that this diacritic became this, you're just flipping it. The way you can combine these diacritics is by merging them such that exactly one leg of one diacritic coincides with one leg of another diacritic. So, for example, you're not going to merge this diacritic with this in this way because you won't be able to see it. However, you can merge these two in this way, or if you really want to merge this corner here, you can merge it in this way, thus getting a diacritic like this. And these diacritics, the way they are shaped, is specifically designed to allow for easy conversion of inverses. So if you are, well, for example here, resistivity and conductivity, this diacritic is just this one flipped over, and you can say the same thing about any other combination. So if I were to do x times theta over a, we would go with, let's build the diacritic first, actually. So over theta would be this, wait, no, times theta would be this, over A would be this. So we take this leg and merge them together, and we get this. Now the next part of this would be flipping it over. Although this might be a little too easy, I just realized. Let's go for something a little bit more complicated. X times a length per a volume. And so X per volume is this, times the length would be this, so your times length over volume. And with that being said, when we invert this, so we are writing volume over X times length now. We have inverted X, and we will multiply by volume and divide by length. And as you can see, this flipping rule works no matter what. And again, if we want more examples to show that this works, A over X times theta. Again, we get X bar, but then we can also multiply by area and divide by theta. And there you go. As you can see, all the Macon does for the diacritics is just flip them over. However, I would like to do a couple more examples with this. So what happens when you're merging like 3 or 4 diacritics together, let's say. So let's say you're merging this diacritic, so over volume with times area, and let's go times length and times theta. So that'd be X over volume over an area over length times a theta. So if we do this, I will first write this diacritic for over volume, and then I would like to stem the theta diacritic off. That one's easy. And then I would like to set up the over area diacritic and the over length diacritic. And as you can see, there we go. That is the tutorial on how these diacritics work. So let's get back to the rest of the video. I will note we can define capacitance. That is way too fat. Fine. We can define capacitance as the reciprocal of gamma to Q. That will be it for this video. Next video, we will look into concepts such as impulse, jerk, yank, power. So with that being said, I will see you in the next video, and peace.